Welcome to the Future Directions for BACnet Security. This is the third webinar in the series that derived from the BACnet SC Interoperability Acceleration Program, which along with these webinars resulted in the production and release of reference implementation for BACnet SC. So I want to take a minute and thank the program participants, without whom we wouldn't have been able to do this webinar or the underlying program. And if we had an applause track, this is when it would be playing. But since we don't have one, I'll just say thank you personally to all of them who participated, both in terms of the financial support, but also the technical interactions that really made it work. So thank you all. This webinar is one element in the BACnet International information and education content for the community. If you want to see more of that content, check out the BACnetinstitute.org, where you'll find some courses related to BACnet, online courses, as well as a library of white papers and presentations and articles that you can select from, sort through and search through. And finally, a community forum where you can post your questions and get answers from a community of experts. Now, before we start, a couple of quick housekeeping things. All participants will be muted during the presentation. So if you have questions, use the Q&A feature on your Zoom webinar control panel to submit the questions. Time permitting, at the end of the webinar, we'll answer some of those questions. And if there are some other general interest questions we haven't had time to answer on this webinar, we'll post them in the community forum at the BACnetinstitute.org in the next day or two. After this webinar, you'll receive a follow-up email. It'll have a link to this webinar as well as the other two webinars in this series on the BACnet International YouTube channel. And we'll also send you a link to the BACnet SC reference stack, which is now an open source component on SourceForge. All right, so let me introduce our expert speaker for today, Dave Robin, the chair of the Network Security Working Group of SSPC 135. Dave has a whole lot of years of BACnet experience in a number of different roles: visionary, architect, product developer, and one that's not so widely known, which is author. A fair portion of the BACnet specification was authored by Dave over his many years working on the committee. And most recently, through his company, BSC Softworks, he developed the BACnet SC reference stack for the program, Interoperability Acceleration Program. And on top of all of that, Dave's a great presenter and just a good guy. So Dave, take it away.
Oh no, pressure. Okay, well, let's dive right into it then. One of the main things to let everyone know is that for those who know about BACnet SC, it's no longer an addendum to the standard. It's now in the standard. So the big X there, it's fine print, but the X is on the document that says addendum BJ. And the check mark, of course, is on standard version 2020. We did sort of hold off on republishing BACnet until we got the until we got the security standard in there. So 2020 is a big year in many ways, but it was a good year for BACnet because now we have it in there. So the reason I'm saying this is that for a year or so, people have been talking about addendum BJ. Well, BJ says this and BJ says that. We're going to start transitioning to where you're going to hear people talk about Annex AB. So, you know, is it in AB? What does AB say? So AB is the new name for BACnet SC now that it's in the standard. So this is a review of what we've covered on the former webinars, just to kind of get caught up. BACnet SC was designed to be just another data link. And we did that intentionally so that you could plug it into the bottom of an existing BACnet stack with very little impact. We tried to make as small a impact to the rest of the BACnet ecosystem as possible. And so BACnet networking, the network routers all work the same. The application layer, segmentation, all that stuff didn't get changed. We can send really big APDUs now if you're on the same data link though. So we did make that change. But in general, it's just another data link. like MSTP or Ethernet or any of the others. And so it plugs in the bottom of the stack. But the difference is, of course, that with Ethernet, there's like zero configuration because your Mac just comes with the hardware, right? IP, you might have to check a box that says whether it's DHCP or whether it's a static IP or something like that. But with BACnet SC, there's a little more to it. So this slide just mentions the fact that there's some additional tooling for certificate management and provisioning and things like that that need to go in it. The middle bullet point there says the details are not in the spec yet. Yet in parentheses, they are. We have worked out in great detail. The IT working group has been meeting every week for a good part of a year to work out the details of interoperable configuration of BACnet SC, certificate management particularly. And that is now out for public review. So please, if you're interested in it and plan to make a product around it, by all means, look at that public review and give us some comments on certificate management. So that'll be an extension to the network port object. Right now, it's a proprietary extension to the network port object, so you can do it in any protocol revision. And that's what the second to the last bullet point there says. It can be put on any protocol revision, and that is also a first for BACnet. We've never done that. But to spur adoption, we wanted BACnet SC to be plugged in to an existing stack and not have to rev the entire stack up to the latest protocol revision. So now the best thing about it is that we added a new capability that we've never had before, and that is the ability to carry extra data along with an existing service. So services have never been extensible. Some of their classic service read property, you can't just throw extra stuff on there. Even in a proprietary way, you can't add extra arguments to the read property service. Well, with BACnet SC, we fixed that. And we made it an extensible way of tacking on additional data onto the classic services that has huge impact. And we'll see that in this seminar. That's actually the main point of this seminar, is to talk about the capabilities that this newfound ability to have data tag along with classic services will give us. So as I mentioned, the protocol revision independence was made to drive early adoption. And this slide basically summarizes what I've said about the network port object. So that's called addendum CC. Eventually it'll be in the standard. Of course, we'll drop the CC moniker at some point, but for now it's called addendum CC. So please go look at that. Now, this is what I was talking about. This is the key addition of BACnet SC that enables the future. We can have extensible data tacked on to any APDU or NPDU. So application layer messaging or network layer messaging can have these extra data on it. Now, for a long time, and I said everyone used to ignore this because for a long time, there was a parameter in the stack called security parameters. Oh gosh, it's been there for 10 years that nobody ever used for anything. Well, we expanded that. We renamed it. That's why they cross out in the attributes. We renamed it to data attributes and put security parameters inside, but also generalized it to be more than just security. But today we're going to talk about security, of course, because that's everyone's favorite topic. So this data options is in the BVLC message. We don't need to know what BACnet virtual link. It's a acronym that you probably don't need to know, but it's the way of conveying a network message in either a network layer message or an application layer message. We now have these data options that accompany the payload all the way to the end, as long as it's going through an SC aware network, of course. And we'll see how obviously it can't go through a classic network because it doesn't know how to convey them. So, but we're going to use that to our advantage. So we also said that we have no idea what these are going to be used for. We know they're probably really useful, but we don't know. So we're going to make a requirement right off the bat that if you're a router, you will route 4,000 octets of these options, even though your maximum message size is 1,500 bytes or 1497 that you're normally routing. We're going to say, yeah, you got a 1497 message, but we'd like you to carry an additional 4,000 octets along with it because we really don't know what we're going to do. So we're reserving room for the future. What we're going to talk about today is nowhere near that big, so don't worry. So what do we do with data options? Well, the first one is already in the standard. We created it. It's called Secure Path, and we tack it onto a message to let the recipient know that the message originated in a secure device. It passed through a secure hub, a secure router, maybe another secure hub, and it finally got to another secure device. And along the way, it never left. So it's called Secure Path for that reason. And it's our first data option that we put on all NPDUs that we send. So what does it look like? Here you can see what I just said. A device A hops to a hub, hub goes to a router, router goes to another hub, and then finally to device B. And the Secure Path little tag on there, the blue message is, of course, the NPDU or APDU. And the little tag there indicates that we're adding some extra data to it. And it makes it all the way through to the end. And so when B receives that message, he goes, oh, this originated with a secure device and it never left the secure tunnel. So that's a good thing. Now, what happens if it does leave the secure tunnel? It goes to classic IP, but it goes right back to SC. Oh, yeah, it's okay. We're going back to SC. That's an SC device, but it left the tunnel. So when it goes from SC to IP, the little secure path tag goes away. So then the message changes character to orange here to indicate that when B gets this, B is getting the message over BACnet SC. He's getting it through a secure channel, but it wasn't secure all the way. So he doesn't fully trust it. So B can make the decision as to what to do with that. Likewise, of course, if you have a router and it's routing from MSTP, device C down here in the corner never had a chance to apply the secure path because it's on MSTP. So when the router sends that message on, it's also orange and doesn't have the little tag, but the blue stuff does. So now you can see B gets to make a decision based on whether it came from a secure device and went through a secure path or not. So that's a good thing. Secure path was our first one. It's built in. So what? What do we do with it? As I just said, the secure path indicates that the device was given an operational TLS certificate. It's on the network. It's an SC device, and it never left. Well, that is a big deal. The recipient can know that it didn't come just out of the blue. It didn't come from an unauthorized device or somebody that snapped onto MSTP or Ethernet and sent a packet. So it's important. Basic authorization decision. But what does basic authorization decision mean? Secure path is a single bit of information. It doesn't say anything about the originator other than it's one of us. It doesn't even say that it's, specifically device 123. It just says it's a device at MAC address blah, and it sent you something. So that's pretty good, but we want to go beyond that. So that's the point of today's discussion is future direction, and secure path, it represents the present, which is great, huge advance over what we had. I mean, unbelievable. And I guess the rest is just kind of nuances beyond that. But BACnet SC and the secure path are a giant step forward. But let's see where we can go from there. So you can't make decisions based on the MAC address because that could change. You can't make the decision based on the device ID because the device ID is not in the message. When somebody sends a read property, it doesn't give you a device ID. So there isn't much you can do other than just say it came from one of us. So now let's do better. Let's take it and find out if we can find out where the message came from, really authenticate the sender as opposed to just one of us, one of the group. We'd like to know who sent it. And device ID is our most likely candidate because anybody who knows BACnet knows BACnet device object property reference. Actually, I should have made it even longer. BACnet device object reference there, but we rattle off our tongue BACnet device object property reference all the time because we use it to point at things. We point at devices and properties. And we do it with device ID. So device ID would be the natural thing that we'd like to say, hey, I am 123 and I'm sending this to you 456 and it's only for you 456. If it goes anywhere else, it's wrong. So device ID is very important and it's simple. People already understand it, and we're going to extend that to be the concept of the identity, authenticated identity. Now there's in this presentation, please forgive me if I mess up the words authentication and authorization. I'm going to try and be very careful on that. I even have a slide on that, but there's a huge difference, of course. So authenticating says, who is this? But in addition to authenticating the device, there's also a human user, and possibly a human user. Light switch, you don't know who the human user is. There is, but we don't know who it is. But on a workstation, there's obviously somebody signed in, and we'd like to record that information too. So we will get to that as well. Now, we could say, okay, if the sender is properly authenticated, so I know who's sending it. So what do I do with that? Now device B not only knows its secure path, but he knows it's a secure path from device 123. Well, the bad thing that could happen is that every vendor, every product maker creates local policies in B, which says, okay, device 123 can do this and he can do that only if the user ABC is logged in and blah, 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 blah. So it could go down a really bad path where every device takes the information of who sent this message, but then has their own access control list, their own local authorization policies. And we're trying to avoid that. So enter what we're currently doing in the Network Security Working Group. We're trying to take this to the next level of authentication and authorization. Secure path, as I said, was the first step, but we need to go beyond that. We need to provide authentication, as I said, which is who is sending this, possibly what user, but most importantly, which device. And then what are they allowed to do? And who says what they're allowed to do? And I don't want a policy in every VAV box out there that says who can do what. I want that to be, well, we need that to be more universal than that, and somehow have the end devices just go, oh, look, I see the permission. And we'll get to how that all works. In a minute, we're going to talk about how the internet handles this, and then how we take those internet standards and move them down into BACnet. So here we are. How does the internet handle this? The most common way today, and it's just ubiquitous. I mean, pretty much everything is funny. Just the other day, I typed in something and it redirected me to a URL. And in the URL, I saw the word OAuth. And so everybody is using what's called open authentication now to do it. And open authentication 2 is the version that everyone's using. And it's a 3-party system. It basically allows, and I don't need to talk too much about that because I have lots of pretty graphics coming up. So if you're tired of looking at text, wait like one more slide and we'll get to some pictures that make all of this make sense. So OAuth is an authorization scheme. It's not really used for authentication, although OpenID Connect is a form of authentication. If you do single sign-on where you go to a website and it says, sign on with Facebook, sign on with Google, sign on with Apple, right? All those choices where you don't have to create a new identity and a username and password, that's probably using OpenID Connect, which is a way of a standard for single sign-on. And OpenID Connect is built on top of OAuth, kind of just out of convenience. It says it is taking the authentication frame, the authorization framework, and using it for authentication. But in any case, OAuth 2 is the thing. Now let's see how it works. Okay, here we go. Alice says to the Songs R Us server, whether it's Spotify or whoever you're talking to, it says, hey, play Bob's songs. And this, of course, the internet server is going to say, no, who the heck are you? So Alice says, okay, hey, Bob, give me your password. And of course, the joke here is he says, what is this, 2010? No, I don't think so. And by 2010, I mean, that's about when this open authentication stuff started really taking off. And we had this 3-way thing where, no, I'm not going to give you your password. Even though that's what you would have done. And there's plenty of apps out there. Believe me, there's everyone's got apps on their phone that still ask for your username and password in order to do things for you. And we don't want to do that. So PayPal was invented to avoid that for payments. And OAuth was created to allow something like this to work without having to give out username and passwords. So instead, Bob goes to a different thing, the Songs R Us authorizer. It's a different computer, and says, hey, let Alice play my songs. And so Songs R Us says, okay, Alice, here's a key. And it gives a key to Alice. Now, Alice says, play Bob songs. And the server says, great, great. So you see these two on the right, the Songs R Us server and the Songs R Us authorizer working. That's the same company. They work together. So that's not really 4 parties on the screen. You see there's 3 parties here. There's Alice and Bob and Songs R Us. So now when Alice says play Bob songs and he provides the key that came from the authorizer, Songs R Us server goes, I know that key. That came from the authorizer. I like this key. That's going to open the door and let you play the songs. So it says, okay, and plays the songs. But now she says, hey, change Bob's profile pic. I want to put antlers on him. So no, can't do that. Why not? I'm sending you the key. That key is good for playing songs. So these are custom crafted keys. These are not just username and password. So then she says, hey, Bob, I know you don't like technology, so let me take care of you for you. So Bob says, okay, goes back to the authorizer, says, let Alice manage my account. That's effectively the same as saying, give my password, but I'm not giving the password. Says, okay, here's a golden key, gives to Alice. Now the golden key says, change Bob's password. Says, okay, you can do anything because you have the golden key. So then she accidentally deletes all of Bob's songs. And the server says, okay, you have the golden key. So this is a good lesson in that keys and authorizations should always be least privilege needed. Alice doesn't need a golden key. She just needed a key that would let her do songs and profile. So also, golden keys sound dangerous, don't they? Well, yes, in OAuth 2, the common use is a bearer token. And a bearer token means if I hold it, I can do it. I am given it's like a physical key. And that's why I chose a picture of a key. These are actually little signed certificates and digital signatures and all that stuff. But for the purpose of this discussion, I used the idea of a key that you could drop on the ground and somebody could pick up. So bad actor steals it and does bad things with the golden key. So you have to protect these keys. So let's fix that. Now Bob says, hey, I don't want to give you just out a key that can be dropped. I want only Alice to play my songs. And so the authorizer creates a key with Alice's identity in it. Now only Alice can use that key. So Alice could drop this key on the ground and nobody can pick it up. So let's see what happened. Alice says, play Bob songs with this new identity key. And the Songs R Us says, prove that you're Alice. So somehow Alice has to present additional proof, some other form of proof that says that she's Alice. And then the server says, okay, you can use that key. So this sounds awfully familiar. If you look at this scenario here of presenting something, being challenged to present something else, let's tie it all together with, instead of over the internet, you're going to a store. Alice says, I want to buy something big. Here's my credit card. And the shop says, that's a nice credit card. It says Alice person on it. How do I know you're Alice? Prove you're Alice. So Alice then presents the driver's license. And then says, okay, you're Alice, and then lets you do the purchase. Now, so think about how that chain worked. The name on the card that I presented says Alice. The name on the license says Alice. The picture on the license is a picture of a face, and Alice is standing in front of you with her face. So that's how it all ties together. Probably haven't even thought about that chain, but that's how that chain works. And that's how the shop knows to trust the card, because it went all the way back to Alice's face, which is something that she presented and completed the loop. So that's how the internet works. Now let's talk about the actual terminology of OAuth 2. Alice in this case is the client. Bob is obviously the resource owner. He owns the resource, which is the songs. The songs are coming from a resource server, which is the only place that holds the songs. And then the thing that's making the authorization decisions and crafting those keys is the authorization server. So now, in reality, chances are Alice is not a human. Humans don't shout into the internet, hey, play Bob's songs, right? So there's computers involved. So let's replace Alice with a server, smart speaker server, like an Alexa device. Alexa server, the back end, that's Amazon on the back end, conveniently Alice and Alexa and Amazon. So this client becomes an actual server on the internet, as well as the Songs R Us server on the internet. So the whole scenario, you replace Alice with an Amazon server, and the resource owner is actually the third party here. And he's telling his smart speaker, hey, tell Amazon to ask to play my song. So replace Alice with Amazon, and you get a real life example here of where you have, this can actually work. You don't have humans shouting in the wire as before. So those are the players. Now that's great. So that's all OAuth 2, and we've got internet and HTTP and stuff flying around. But what are we going to do for BACnet? That is a huge internet-based scheme, and we need to fit it into a very tiny environment. So a group within the IETF, which is the people who created all those OAuth schemes and everything, and the keeper of all the RFCs that those are defined by, created a new group called Authorization, get that right, Authorization for Constrained Environments. And it looked at a bunch of different ways of doing things, and eventually ended up patterning it after the well-proven OAuth. I mean, they started out with no rules. The authorization for constrained environments could just make up anything they want. Well, first rule of security is don't roll your own security. And the OAuth was a well-vetted, well-implemented flow that everyone understood. And so eventually ACE work became how to take that and squeeze it into a thimble. How do we take the OAuth that was built for an unconstrained internet and put it into something that I can put in a light switch? So that's what they did. And we'll see in a minute how they did it. But it's not quite an RFC, but it is in its 45th revision. My slide's a little behind. The last couple of days, it's been revised. So it's been through last call and all that stuff. So it's on its way to becoming an RFC now. But it is a framework, and we'll see how that works. So the ACE OAuth framework, the small version of OAuth, does offline token validation so that the resource server doesn't need to talk to the authentication server to check out the token. It has very compact encodings. Instead of JSON, it's something called CBOR, which is compact binary object representation. It's a compact binary form of JSON. It does token caching, so I don't have to send you the token every time. So look, I'm going to send you a set point every minute for the next, ever. For it, don't make me send the token every time until it changes or expires. So that's important. And one of the more important things also is I don't have to know ahead of time how to get a token or what to ask for. I simply try something, and if you say go away, you tell me a hint as to who to talk to and what to ask for. And we'll see how all that works. So it's a framework. It's not a protocol. The ACE OAuth framework is not a protocol. It only specifies how things flow around. The individual protocols will define that. So that's the next slide. We talked about profiles, and the profiles actually put this into bits on the wire. And there are already profiles in the works, very mature, on their way. Most of these are in last call. The DTLS version, which is the datagram version of TLS, small instead of TCP. OSCOR is object signing for end-to-end security. MQTT, there's a profile for that, for using ACE OAuth to talk to MQTT servers. And we're going to talk a lot about an ACE profile for BACnet. So what would an ACE profile for BACnet look like? Well, instead of using CBOR, which is, as I said before, a binary representation of JSON, we would likely use ASN, because putting in CBOR, well, JSON's too big, and putting in CBOR parsers and generators in every BACnet product when we already have a tagged mechanism for tagged values, using ASN would be silly. So we'll create a version of CBOR using ASN. We'll use BACnet APDU services instead of HTTP. And we'll use our own ways of defining it, and it's all defined in standard 135, so you don't have to go running around to a bunch of RFCs or a bunch of other external documents to figure it all out. So hopefully that will be familiar to us. It will look and feel like BACnet, but it will inherit the proven security aspects of a well-vetted framework of ACE, and which inherited the framework of OAuth. So in ACE OAuth, here are the players. Notice the client is no longer a person, no longer Alice. It's now a device. And the resource server is no longer a big amorphous Songs R Us thing on the internet. It's another device. So client and resource server are both devices. Now the authorization server is still a PC somewhere, a PC class device, because it's got all the policies of what can the client say to the resource server. And of course, the resource owner in this pattern is basically the building owner, the person in charge of everything. Now in ACE OAuth, there's also the concept of an identity that's used for authentication, because ACE is an authorization protocol. So there is an identity that's needed, but ACE doesn't talk about that. So now let's talk about BACnet. BACnet does specifically talk about the identity server. This is in our scope because we don't want to leave anything out. We need to actually make interoperable protocols from top to bottom. And BACnet also has the concept of multiple users on a client. So the client might be multiple humans on a workstation or a web server, whereas ACE really just considered device to device. So, but don't be scared. This looks like a lot of new players and a lot of new hardware and a lot of new servers and everything. In simple BACnet systems, this might all be the same. The resource owner is the client, and the owner and the building operator, and the identity server and authorization server, put it in quotes because those are really just functions within your big workstation that you might already have. So we broke them out as separate functions so you can see how they interact and play with each other, but it doesn't mean you have to install new PCs. All right, now currently BACnet. Now we're back to where we currently stand with BACnet. BACnet SC provides certificates that come from yet another PC that we hadn't talked about. It's only going to appear on this one slide, but the BACnet Certificate Authority, which might also be built into that workstation for simplicity. But Certificate Authority is another process that gives out certificates to the different devices. And that's where we stand today. Every device gets a TLS certificate, and in the certificate is the public key that he uses to communicate with, and a subject identifier of some kind of a name, right? That's like the Alice person on the credit card. That's the name that indicates what this device is. So that's today. Now, great, we have that. So these two talk to each other, and client says, "Hi, I'm device 123," and the other guy says, "I'm device 456." There's really no proof of that. I know you're one of us. I know you have a certificate, but I don't see 123 in that certificate. I see ABC. I see a subject name. I don't see your device ID in there. And we don't want to put the device ID in the certificate because this certificate authority could actually be something that we don't control. This might be an IT department's certificate authority. We don't necessarily control that. We don't control the certificates. So we can't dictate that stuff like device ID be in the certificate. So here's how we're going to solve that problem. Just like Alice with her credit card and the driver's license were two different things, we're going to provide two different things here. So now a BACnet identity server, that's our server that we control. That's not the IT department. We create tokens, these little identity tokens, and the identity token ties, this is like the driver's license. The identity token ties the subject name to the device ID. So now on a later slide, I'll see how well that all ties together. But basically when the client says, "I'm device 123, it presents the token that says 123, which ties it to ABC. And at the same time, he presents a certificate that says, "I'm ABC and I'm using this key." So the whole loop is closed and the recipient knows, okay, you really are 123. So now I'm going to go through this kind of quickly because we've got a lot of slides to go through and not a lot of time. But today we exchange certificates and then we start talking. We do a connect request and a connect accept and life goes on. Tomorrow, when we finish all this, we will exchange certificates, then we will exchange identity tokens so that both sides know who the other one is and has an actual device ID associated with it now. which is a really nice shorthand from now on. Now that I know your device ID, it's a really short, small number that we can use in all future conversations. So when both sides talk to the hub, they send these two things together, and the hub learns, oh, A is 1, 2, 3 and B is 4, 5, 6, and life is good. So now here's where I mentioned the binding path, as in the example of the license going, credit card going all the way through the face, you know, here is the same path. We have a subject in the token, subject ABC in the little gold token, ties to the subject in the certificate, that's like Alice's name on both of them, ties to the public key in the certificate, which is like her picture of her face on the, and that ties to the private key that's actually used to establish the TLS connection, which is kind of like, here I am, this is my face, see it? So we've got the chain, and now we've tied it all together, and I know for sure that that is device 1, 2, 3. The nice part about this is that these certificates, that both the certificate and the token, are public knowledge. You can drop them on the floor. You can't use either one without the private key that's built into the device. So certificates are not safeguarded. You don't have to protect them. In fact, you give them out freely when you make a conversation. Say, hey, you, here's my certificate. And likewise, you can say, and here's my token, my identity token. They're not secrets. They're all tied together in this chain to the thing that is secret, which is inside the device A and device B. And they use that secret to create the TLS channel. And that's how it's all tied together. So these are public documents. So also, of course, the hubs, those guys learn the identity of the hub mutually. Now, another thing is you've got a B device over here that doesn't play this game. He's got the SC certificate, but he doesn't have an identity token. So the hub knows, okay, you're one of us, but I don't know who you are. So we'll just say that you're old, or your unknown device ID. So this is all part of what you learn as you establish with this new protocol. And likewise, an old hub, these guys learn, okay, the hub is old. He's SC, but not identity aware. So how does this work? Now let's go back to data options. Data options, as I said at the beginning, probably slide 3, is the big enabler here, because you can tack these data options onto any message. And here I've got arbitrary ones, foo and bar, and they run all the way through the end. And A sent foo and bar and B got foo and bar, and that's great. And the routers are required to route a whole bunch of it. So now what can we do with this? Okay, we had secure path. Now let's add another one. Now I'm going to add device 1, 2, 3 to it. So you might say, well, why isn't the hub adding that? Because the hub is like, why isn't the hub vouching for it, right? And why don't we have a vouched for device ID as an option that goes to the right-hand side, but not the left? A seems to be claiming his own identity. Isn't that a little suspect? I mean, can't A claim to be something he isn't? Yes, and we'll see how we deal with that. But the reason it's there from the start is that the hub doesn't, if the hub approves it, the hub doesn't have to modify the message. We're really trying to make hubs high performance. We don't want messages to be modified and restructured as they go through. So the device starts the claim, and we'll see if it's agreed with. So here we go. Device A says, I'm 666. And the hub goes, no, you're not. And it won't propagate that. It basically blocks it. But for auditing reasons and for reasons of not wanting to restructure the message, we actually just exit out in place. We deactivate that option as it goes through. So the device ID option is still there in the message, but it's been marked as invalid. So device B goes, okay, I'm going to audit that this came from a 666, but I'm not going to pay attention to it. But for auditing reasons and for Wireshark and whatever, we can see it go through, but it's been neutered, it's been deactivated. Okay, now what about an old hub, right? This is an evil A, but the hub blocked it. Well, the evil, if it's going through an old hub, it gets there and says device ID 1, 2, 3, but now B says, you came from an old hub, so you wouldn't have blocked a bad one. So I don't trust it, so I'm going to ignore it on my end when I get it. So we've thought all this through about how things get trusted and ignored. And so now we've got that. Great. What's next? Now we got back to this same old problem. Okay, it's secure path. I know who it is. So I'm going to have my little local policy here. B's going to say, okay, I'm going to accept configuration from 123 and control from 247, and I can restore only from device 777. But again, not interoperable, not standard. So what do we do about this? Add OAuth, add ACE OAuth, but add OAuth. Now B only says, I'm not going to have any policies at all. If somebody presents me with a control key, I'll do it. If somebody presents me with configure, I'll do it because I trust that he's been given that. And of course, the keys are bound to the sender, so they can't be dropped and reused by somebody. So let's talk about what happens if you try to do something you don't have a key, you don't have permission. You say write property, and B says, nope, you didn't present any authorization. So I'm going to tell you where to go. This is very helpful information. Instead of just saying error, you figure it out. I know who B knows who the authorization server is, and B knows what to go ask for. So in the hint, he says, go talk to authorization server number 555, it's device ID again, and ask for configure, because that's what you're trying to do. You're trying to write to a configuration property. So now A goes to 555 and says, hey, I want to, quote, configure device 456. And authorization server consults his policies. Yes, device 123 can do these things. Great, generates an access token. We've been calling the, in the pictures, we've been using little pictures of keys, but because in the security world, key is always used, usually means encryption keys and stuff like that. They call these access tokens. So the things in the OAuth world are actually called tokens. So the access authorization server creates an access token and binds it to A, so only A can use it. So this little blue key with an A on it now can be dropped, and it's public information. And it has an expiration time. So now, one thing to note, this looks like a critical point, single point of failure. Authorization server looks like if the authorization server is down, everything stops. No, we have, as we do in BACnet SC with redundant hubs, we have redundant authorization servers. So if you can't talk to 555, you go talk to 556, because you're given both in the hint, just to let you know that we've covered redundancy in this. So now with that newfound access token, he goes to B and says, presents it, and B now says ACK. So now what I didn't show on here for just keep it not so noisy visually, of course, B also needs to know secure path and 123 because the token is bound to 123. So it's bound to A in this picture, but A means it's the inside the token. It actually says 123. And so both of those other pieces have to be on the wire too. Now, I'm going to send you this over and over and over and over again. So please remember it. So what happens is A sends this token to B, in addition to the write property, in addition to the ACK, he sends back, oh, by the way, yeah, I had room in my cache. And so I saved that key you sent me, and it sends back just a little tiny identifier of the key. Next time, A just sends the little tiny identifier instead of the big key with the signatures and all that stuff. And if B still has that in his cache, B uses it. So this is an example. This is one of the extensions that ACE OAuth did, whereas OAuth doesn't do this. OAuth sends the big token every single time. This, if it's cached, then we just send the reference to it. So groups, I'll cover this quickly because it's kind of complicated, but basically same idea. It says, hey, I want to control a group of devices, and you get back a key that is bound to you, but it now addresses a group. Instead of addressing device B, it addresses group 42. So let's see what happens. I take that thing and I send that same exact access token to two different devices, B and D, and B says, oh, I am 456, but I'm also a member of group 42. So I will accept that key. And the other one says, I'm a member of 42 and 77. So I will also accept that key. So you can see how group tokens work pretty easily as well as individual tokens. So let's talk about multiple users, because that's an important thing. You notice we added this thing in the middle for BACnet that ACE OAuth does not cover. So we have these multiple humans possibly associated into one client device, but it probably looks more like this. You have multiple authorized users over there on the side talking not BACnet. That's the orange. The orange indicates in this case that it's like HTTP or something to a web server, let's say. And the web server is the client now. So the client is not a person or even the person's laptop. It's another device. It's a server. It's kind of like the Amazon Alexa server out there on the internet becomes the client, assumes the role of the client. So when it comes time to say something, Alice says, hey, do something. It has to go to the client, the server now, it goes to the authorization server and says, hey, Alice wants to do something. Give me a key bound to me and Alice. Now you notice for the first time, the key that comes back, the little tag there, has two indicators on it. It has the C indicating that it's bound to the client, but it also has a little picture of Alice on it indicating it's bound to Alice. So now when the client goes off to the resource server, it sends that token with both C and Alice on it, and the resource server can log that this, right, I'm going to agree, I'm going to say yes, but I can log in my audit logs, this message came from that client machine and on behalf of this client, on behalf of this human. So, and of course it remembers it, so it doesn't always run off to the authorization server. The little box down below the client says, I'm remembering this key. So obviously when Bob comes and does the same thing, then the multi-user client remembers Bob's key and will use that every time Bob wants to make a request. So that's how that works. One final thing to talk about is that everything we've talked about so far is that the A device goes off and talks to the authorization server and gets the key. And if A is a light switch, that might be kind of a burden, right? So there's a possibility for a helper application to ask for a token on behalf of somebody else and give it to A, and then A can use that. So A can be a very small device. Everything we've shown up until this point looked like A was managing everything and doing its own thing, but there can be helpers here because the tokens are not secret. They're bound to A. So you, when the authorization server gives the token to the helper can't use it. Only A can use it. So this is a secure flow, even though all of these documents are public. Okay, so what do we have? What has BACnet SC enabled for BACnet? Well, as we said right at the start, this ability to carry data options is the key. So far in this presentation, we've introduced the concept of an identity token, which is handed. Notice when the reason I showed that the connect sequence, you had the connecting with the TLS connection with the certificates, then you had connect request and connect response, right? Those are existing messages. What we did is we put the identity tokens on those existing messages. We did not create new messages. We didn't have to create a new identity connect request. We just did the same exact connect request, but we tacked on an additional piece of data to it. So data options go even, well, it's tacked on technically for those who are paying attention, that's tacked on as a destination option, a little bit different than data options. So just to be clear, same idea though, we can tack on these same options in either of two different places. One of them goes all the way through routers and one of them only goes to the next hop. So the connection option is to the next hop. So we've talked about identity tokens, device IDs, the inactivated device ID, the hint that comes back, the access token that I give you, the message that says, I got that access token, you only need to send the reference, and then of course, the reference. So those are what we've got so far. I'm sure we'll have more in the future. Which brings us to the inevitable last slide. All of that I just said is work in progress. It's fairly well along. We're having meetings on this every 2 weeks. And so every 2 weeks, we have a big discussion document, which is now very long and includes conclusions. Well, at the end of it, of course, it shows everything we've decided in the past weeks and the changes we've made over time. And then it's basically showing a direction of where we're going with all this, but it's work in progress. Please join the Network Security Working Group and join us. Our first principle, of course, is don't roll your own security. It's what everyone will tell you when you're doing a secure protocol. Always look to best practices first, and that's what we're doing. So our guiding policy in network security is to try to use RFCs to the best ability and making them natural extensions to BACnet so that they don't feel jarring. We're not adding JSON, we're not adding CBOR, we're not adding HTTP or COAP. We're doing everything in BACnet using native BACnet ways of doing things, but we're looking to the security aspects of the RFCs and profiling those down without harming the security aspects, of course. And of course, that's what a security review is to look and make sure you didn't break anything in the process. And in fact, the ACE OAuth framework, part of its life cycle was to be reviewed by the security experts to make sure that it didn't break OAuth. And likewise, the CBOR versions of CBOR web tokens for CBOR access tokens was carefully vetted to make sure that it didn't break the already established JSON web tokens that are being used by OAuth. So we will have to do that same thing. And hopefully I can enlist some review from the IETF folks as well to make sure we didn't break any of their RFCs in theory, even though, of course, we're doing it in the BACnet way. So that is it. Please join us in the Network Security Working Group and the IT Working Group. As I said, goals, dreams, constraints, insight, experience, and review of what we're doing. That's it.
That's great, Dave. Thank you for that. We have time for a couple of questions, and a couple have wandered through the Q&A things. Let me pose a couple of those to you. One of them from Ralph was, if everything's encrypted and signed, why do you care about a secure path indicator?
Oh, that's a very good question. Because it's encrypted and signed in SC, but if it ever leaves SC, then it basically, it was that slide that showed SC and then an IP segment and then another SC, right? So the end device got it from an SC peer, but it originated from an SC peer, but in between it went through IP. So it's not a secure path because somebody could drop into IP and inject something that looks secure, but when it gets to the far end recipient, he needs to know that it came all the way through and never left. So yes, A to B, absolutely, you don't need secure path because duh, when you're doing direct connect, I can see you, I'm talking straight to you. So it's not necessary, but the secure path was designed for routers to let you know that it never left SC.
Great, great, thank you. Sort of a follow-up to that, and maybe down the same vein, from Lorenzo was a question early on about, since BACnet SC uses TLS and WebSockets, which are IP sort of things,
right?
Are we going to see BACnet SC supported on MSTP?
Yes and no. MSTP as a physical data link, yes, because there's actually an, if you want, we haven't seen it yet, nobody's implemented it yet, but it's a physical possibility. MSTP was extended to 1500 octet frames back several years ago, I guess 2 years ago or whatever. So we extended MSTP frames to be full Ethernet sized frames. So you can drop on 1500 byte frames onto MSTP. That was step one. Step two said, hey, now that we can put full 1500 octet frames on MSTP, let's make a version of IPv6, compressed IPv6 that runs in those frames. So I can take an IPv6 frame from Ethernet and drop it right onto MSTP. So that is in that, and that's an RFC. 80, I better not quote it. There's almost 10,000 RFCs now, so my brain cannot hold them all. We're well into the 9,000s now. So one of the 8,000 series RFCs was an RFC for IPv6 over MSTP. So in that sense, when you're doing that, you can actually coexist because MSTP as a BACnet data link as MSTP is riding along with IPv6 frames on the same wire. And those IPv6 frames would just be BACnet IP. And then you can either use BACnet IP or you can use BACnet SC. So it is IP, basically IPv6 on MSTP. So that's the answer. People may or may not do that. but BACnet made the 1500 octet frames. The IETF defined IPv6 over MSTP. All the pieces are in place for actually doing full TLS, bridged, routed from Ethernet to an MSTP data link.
I'm glad that question got asked because that was not an obvious answer.
Yeah.
Here I'm looking for a one-word answer, and now we actually understand a little more of the subtlety. So thank you. That's the value of having you here and not me as the presenter. Another question from very early in the presentation. At one point early on, you said that the extra data that's been defined as a part of BACnet SC gets carried along with classic services. So which BACnet services are classic?
Yeah, it's basically, it's carried on along with an NPDU. So that's every service, network layer service. APDUs are inside NPDUs. So you have an application service like read property is inside a network layer message. Network layer messages like who is router, and application layer messages like read property, those are both NPDUs, and the data options apply to the NPDUs. So they can go to any of those, every BACnet message.
Good. Another question that came up that you sort of touched on with your light switch statement was how small a device can really do this? Because it sounds like there's a lot of stuff to do, and maybe helper apps are useful, but can you really get down to the little tiny micro computing that has to happen in little tiny devices?
Well, yes, and that's if you can do SC. So I mean, you've got to have the secure tunnel. So if you can do SC, which means you have a X509 certificate and you're doing TLS and you're doing encrypted TLS. You're doing TLS and TCP and WebSockets. If you're doing that, this is trivial.
Should I ask you if you can do that in a light switch?
Oh yeah.
Okay.
I mean, there is, we're not quite to the constrained world of needing to use DTLS. We could, but we just thought that would confuse the market. So we're aiming sort of to, $30 light switch, not $5 light switch. But basically this can all be done with very inexpensive chips these days.
Okay. A question from Ignacio. How do you determine what is a secure path?
Right now, we only have one data link that supports secure path, and that's SC. So we can go from SC to SC to SC, that's secure path. If you ever leave that and go Ethernet, IP, MSTP, whatever, you're not secure path. Now, that's not to say the reason we called it secure path instead of SC path is because we do anticipate other data links in the future. And theoretically, once this all settles down, we could create another version of SC based on DTLS for very small devices. And that would also be secure path because that would be a secure network. So SC is not the only secure network, it's just the first.
Wonderful. Thank you, Dave. We're getting to the point where we probably need to wrap this up. So let me, first of all, thank you, Dave, for sharing your expertise and insight with us. It's been very enlightening, and you keep on entertaining besides, so we appreciate that. For our audience, you will receive a follow-up email from this webinar. It will include a link to the 2 previous webinars, as well as this one, as part of the BACnet International YouTube channel. And you'll also get a link to the BACnet SC reference stack, which, as I mentioned, Dave developed in SourceForge as an open source project. Just a reminder, for more BACnet information and educational content, check out the BACnetinstitute.org. Thank you all in the audience for joining us for this webinar, and hopefully we'll see you again in a future BACnet International webinar and event. Have a great day.